Now let's look at the periodic table. So with the periodic table, we have two scientists who came up with it or helped the process, Dmitry Mendeleev and Lothar Meyer. Now Dmitry Mendeleev gets most credit for it. They were actually both working on it independently at the same time and came up with a similar periodic table, proving the great organization of the periodic table that we still use today. Now the periodic table is listed by increasing atomic mass. So if you're looking at a periodic table, you'll know it goes in order of the number of protons and the order of the atomic mass. It's also arranged so that elements with similar chemical properties are grouped in the same column, and we'll look at that more closely as we go on. The noble gases, for instance, are in the very last column of the periodic table. These noble gases all share the same property of inertness. What this means is they're unreactive. So if you'll look at the periodic table and see that in the last column, helium is the first noble gas in that last column. And that's an element that you might recognize because helium is often used in party balloons. The reason it can be used in party balloons is because it's inert, it's unreactive. If the flame from the candles get near it, it's not going to blow up. Later on, the periodic table arrangement was later justified by the sequential order of the atomic numbers. Remember that atomic numbers is the number of protons present in the atoms of each of those elements. So here's our first picture of the periodic table. I have also posted a periodic table that you could use on the exams if you would like to print that out and have a paper copy to follow as you're working through assignments and exams. So looking at this colorful periodic table, I was just talking about columns. So remember, columns are going to be up and down. We just talked about this last column, the noble gases, that starts with helium here. These columns are referred to as groups or families. The reason they're called groups and families is because they have similar chemical characteristics. When I talk about periods, what I'm talking about are the rows that go from left to right, just like you're reading a book. Notice there are 7 periods in the main part of the periodic table, and that's what we're going to focus on. We're not going to really look at the elements that are down here unless we get into radioactivity in Chapter 9. So here's a picture of the periodic table that I have posted on Blackboard. So what I wanted to point out with this periodic table is you have the periods once again listed 1 through 7 off to the side here. But you also have groups. So what I mean by groups, going down a column. So this first one, these first 2 groups or columns are representative elements. Then we skip over to where boron starts, and these are the other representative elements. So these representative or main group elements we're going to often refer to when we start talking about bonding and valence electrons. So you need to know where the representative or main group elements are located. We'll also talk about the transition elements, which is this group present right here. So here's a list of some special groups present on the periodic table. So in the previous slide, I showed a periodic table and showed where the representative elements were, the main group elements. So among them are the alkali metals in group 1A, so it's going to be that first column present on the periodic table. All of those elements are the alkali metals except for hydrogen. Okay, so hydrogen is not included as an alkali metal. It's actually not a metal at all. It's a non-metal. Next, in the second group, group 2A, are the alkaline earth metals. Skipping way over to group 7A or 17 are the halogens. So this is the representative elements right next to the noble gases. The last group, which we've already talked about, starting with helium, in group 18 or 8A are the noble gases. So all of these special groups are present in those representative elements. The other special group that we're going to mention is that B section where the transition elements are, and those are actually already labeled on the periodic table in the previous slide. So next what we're going to look at are where the metals, nonmetals, and metalloids are. Keep in mind that metalloids are often referred to as semimetals as well. Those two terms can be used interchangeably. So here's a color-coded periodic table pointing out exactly which elements are metals, metalloids, and nonmetals. So you can see that we have a green zigzag line here. The green elements are the metalloids or the semimetals. On your periodic table, hopefully you have it printed out, you can even draw it here, you'll actually see a bold zigzag line exactly where I'm drawing this red line. So the reason that bold zigzag line is there is because it is trying to separate the metals in blue from the nonmetals in yellow. Notice everything touching that line is a metalloid or a semimetal except for aluminum. Aluminum is the only metal that is touching that line. So knowing where that zigzag line is going to help you figure out where the metals are, all the metals being to the left of the zigzag line, with of course the exception of hydrogen. All the nonmetals will be to the right of that zigzag line. And then every element touching the zigzag line is a metalloid. What you will see here are some elements from the periodic table. We are going to label them as a metal, metalloid, or nonmetal based off of where they are on the periodic table. So if you want to do that, I would go ahead and pause it here, see if you can identify them, because the next slide will give the answers to each of those. So you can see the answers for each of these elements. We have the first list here being the group or family that they are in. So notice germanium, is the only element in this list that does not have a special group. So we simply listed the number or column that it is present in. The other elements present were in a special group, so we labeled those accordingly. The next list shows whether they are metalloids, nonmetals, or metals. Now we're going to look at the properties of metals, nonmetals, and metalloids. So starting with metals, metals are generally solid at room temperature. An exception to this, of course, is mercury, which is a liquid at room temperature. Metals often conduct heat and electricity and are malleable, meaning that they are easily conformed. They tend to donate or lose outer shell electrons to other elements when forming compounds, and we'll look at different types of compounds between metals, nonmetals, and metalloids in a moment. For properties of nonmetals, they're gases or brittle solids at room temperature. They usually have lower melting point boiling points, causing them to be gases or liquids. They are poor conductors of heat and electricity. And instead of donating electrons like metals do, they actually accept electrons when forming ionic compounds. Properties of semimetals, they're all over the board. So they're called semimetals because their properties lie between those of metals and nonmetals. So they can gain or lose electrons when forming compounds. They can also share. So we've already defined an element. Elements are present on the periodic table. Elements are made up of smaller particles called atoms. When we represent elements, we can represent them in several different ways. Oftentimes we represent them using a chemical formula. And you can see some chemical formulas below. So an example of hydrogen element, in nature, hydrogen forms a diatomic. So diatomic meaning two hydrogen atoms combine. This is because hydrogen, H, by itself, one atom of hydrogen, is not stable. So it finds another hydrogen atom to bond with to become stabilized. So when we see hydrogen, it forms H2 for the chemical formula, two atoms of hydrogen combined. Now, even though there are two atoms of hydrogen, this is still referred to as an element because both atoms are from the same element. Sulfur does something similar. It forms an 8-atom ring in nature, having a chemical formula of S8. Now remember, this subscript of 8 represents how many atoms of sulfur are in that specific molecule. So there are 8 atoms of sulfur. Since all 8 atoms are of the same element, S8 can be called an element. Phosphorus forms a tetrahedral arrangement, so tetra meaning 4, so it forms P4. So 4 atoms of phosphorus combined. Since all 4 atoms are of the same element, this is also considered an element, not a compound. These elements can also be considered molecules as well. So you'll often hear that term, molecule of hydrogen versus element of hydrogen. Now let's look at a compound. So the difference between an element and a compound is compounds are made up of 2 or more different elements. Okay, so the key here is 2 or more different elements combined. The subscripts following each symbol shows the number of each atom, and we talked about this in the first part of the chapter. So H2O, this is a compound because there's 2 different elements combined. We have hydrogen being one of the elements and oxygen being the other element. The subscripts tell us how many of each. So the subscript of 2 after the H says there are 2 hydrogen atoms. If there is no subscript, we assume there's just one. So there's 3 examples here, CO2 being the next example. That is a compound because it's 2 different elements combined. And then SrCl2, which is strontium with chlorine. 2 different elements combined would make that a compound as well. Now let's look at some different types of chemical bonding in compounds. So when we have 2 elements combining, 2 different elements combining to form a compound, 2 different types of compounds can be formed. One is ionic. The other type is covalent. So how do we know the difference between an ionic compound and a covalent compound? Well, ionic compounds are when electrons are transferred. So we're going to see ions form, and we'll talk a little bit closer about exactly what ions are. For covalent compounds, this is where electrons are shared. Looking at this a little bit closer, covalent compounds where electrons are shared are often called molecular compounds. So those names are interchangeable. So when we're talking about sharing electron, that means we have neutral molecules or elements. To identify it based just off of the chemical formula, look at what elements are in the chemical formula, because if both of those elements are nonmetals, it's most likely a covalent compound. So 2 or more nonmetals combining forms covalent compounds. As for their properties of covalent compounds, they are usually gases, low boiling point liquids, or low melting solids. And this is because they're made up of nonmetals, and we looked at the properties of nonmetals just a moment ago, and nonmetals were often gases or brittle solids. So for covalent compounds, we said that the electrons are being shared. So I have a diagram of that off to the right. You can see we have 2 atoms, the center, blue center being the nucleus where the protons and neutrons are, and then these red spheres are the electrons. So the 2 atoms come close together and they actually share those red spheres, those electrons. Another example below where we have 2 atoms sharing their electrons as well. So when electrons are shared, it is called a covalent bond. Covalent bonds occur between 2 or more nonmetals. Now looking at ionic compounds, we said ionic compounds are formed when electrons are transferred. So when electrons are transferred, we're going to see ions form. So we'll see cations as well as anions. So these are just two different types of ions. How do you know if it's a cation or an anion? Well, a cation is formed when an element loses or donates an electron. So a cation, once you lose an electron, you're going to form a positive charge. Because remember, electrons are negatively charged. So if you lose a negative charge, you would become positive. So one way to remember this is by using the word cation. You see a positive ion. So a positive ion losing an electron is a cation. On the other end, we have an anion. So this would be a negatively charged ion. This occurs when an electron is gained. To remember this, A, and then the N standing for negative, ion. We can actually use the periodic table to predict whether a cation or anion will be formed, and even further for the main group elements, what that charge is going to be. We can do this by using the octet rule. So what the octet rule is the tendency of main group elements to want 8 electrons. So their goal is to get a full octet. Octet meaning 8. So all elements on the periodic table, with the exception of hydrogen and helium, want 8 electrons. They want to be that noble gas, stable state. If they can gain 8 electrons, they're happy, they're stable. So we use this to figure out their charge. So we can actually use the periodic table to predict the charges of ions. Remember, the reason that the elements on the periodic table form ions is because they're trying to get a full octet. They're trying to be a noble gas. Now you're going to notice trends with this. You'll notice that metals tend to lose electrons and become positive. So this is a little counterintuitive because usually when you lose something, that's not a positive. But remember that what they're losing is electrons. And since electrons are negatively charged, if you lose a negative, you will become positive. So let's remember where the metals are in the periodic table. So here's the zigzag line separating the metals from the nonmetals. Remember, the metals are off to the left-hand side, the nonmetals to the right. Everything touching is going to be a semimetal or metalloid with the exception of aluminum. So, looking at the metals off to the left, notice all the charges that you are seeing here are positive because they all form positive ions or cations. The nonmetals then, off to the right, my directions mixed up. The nonmetals tend to gain electrons. So if they're gaining electrons, they're gaining negative charges. So they themselves will then become negative. So notice all the nonmetals to the right have negative charges. Also notice the nonmetals in group 18 here are the noble gases. This is the goal that all the other elements are trying to achieve. The reason those elements have no charges is because they already have a full octet and they don't need to gain or lose anything to be happy. They already are. So predicting charge. So here's a table showing the fixed charges of the main group elements. Notice variable charges in blue here. We're looking at the transition metals and some of the semimetals. So the reason that those are variable charges is because they can form multiple different charges. We can't predict what those charges are based off of where those blue elements are on the periodic table. However, the elements in white, the fixed charged elements, those elements will have that charge to fill their octet. They will have that charge in combination with other elements all the time. So we can predict those charges based off of what those elements are on the periodic table. For instance, in group 1 here, the alkali metals, they always form a +1. So the reason these elements form a +1 is because they're metals, so they like to lose electrons. And in this case, what they have is just one electron to give away. So when they give away that one electron, they then become the noble gas in the row above them. So they have the noble gas state as the noble gas in the row above. Looking in group 2 here, the alkaline earth metals, notice they are always a +2. Why? Because they have 2 electrons in their s orbital. So when they give away those 2 electrons, they become a +2 charge, a +2 anion, and have a noble gas state at that point. Looking over at boron and aluminum. So aluminum is a metal even though it's touching that zigzag line. Aluminum is going to form a +3 charge because it's a metal, it's going to lose electrons, and it actually has 3 electrons in its outer shell. So if it loses all 3 of those electrons, it becomes a +3. Now group 4, we're going to ignore for the most part because they're special cases, but know that group 4 has 4 total valence electrons. Okay, now let's look at group 5, and I'm counting these just the representative elements. Notice I skipped the transition elements. Valence electrons are only applying to the main group elements. So group 5 here is going to have 5 valence electrons. So why do they form a -3 charge? Well, we said all the elements in the periodic table want a full octet, which means they want 8 electrons. So since group 5 has 5 valence electrons and it wants to get to 8, how many more does it need to get to 8? 5 plus what equals 8? 5 plus 3 equals 8. So that's the reason why this group forms a -3 charge, because they're going to gain 3 electrons to their already 5 electrons to have a total of 8. And when they gain 3 electrons, those electrons are negatively charged, so they're going to form a -3 charge. Next, group 16 has 6 valence electrons. The reason they form a -2 charge is because they need 2 more electrons to have 8 to be happy. Next, group 7, the halogens, always have a -1 charge. That's because all they need is one measly little electron to have 8 and have a noble gas state to be happy. So notice the nonmetals are gaining electrons to become negatively charged because they only need to gain 1, 2, and 3 electrons to get there. The metals, the reason the metals don't gain is because the metals only have 1 and 2 electrons. So they would have to gain 6 and 8 electrons respectively to get a noble gas state. And that's a lot of electrons to gain. So instead of gaining them, it's easier for them to lose the electrons they have to get a full outer shell. Then the noble gases have 8 electrons, except for helium, which just has 2. So the charges that we were predicting on the previous slide are also known as oxidation numbers. Some examples of the oxidation numbers of the main group elements that we predicted are shown below. These are the charges on the cations and anions when these elements are involved in ionic compounds. So when they donate or receive electrons, when there's transfer of electrons involved. The reason that these charges exist is because each atom is trying to gain a full octet. They're trying to get 8 electrons in their outer shell to get that noble gas state. So the charges reflect how many electrons that particular element needs to gain or lose to get its octet. So here's just a recap of those charges that we predicted. Remember that those charges are referred to as oxidation numbers. So we're not changing the charges that we predicted at all. We're just referring to them using a different term. So here's a summary of rules for specific atoms. So group 1A, the alkali metals, their charge or oxidation number is always a +1. For group 2A, the alkaline earth metals, their oxidation numbers or charge that they form in ionic compounds is always a +2. Looking in group 16, where oxygen, sulfur, and selenium, they form a -2, so they gain 2 electrons to form a -2 anion. Nitrogen, phosphorus, arsenic, -3. We have aluminum all by its lonesome along that zigzag line. Since it's a metal, it loses 3 electrons to form a +3. And then the halogens in group 7A, their oxidation number is a -1 because they gain an electron. Now atoms, when they're in their elemental form, so when they're not combined and transferring electrons, their oxidation number or their charge is 0, meaning they're neutral. So a recap on ionic compounds. So how do you know if it's an ionic compound? Just by looking at the chemical formula. Well, ionic compounds are formed when you have a metal and a non-metal. Remember, metals like to lose electrons and nonmetals like to gain electrons. And ionic compounds are formed when electrons are transferred. So this is a perfect setup between a metal and a nonmetal. They pair up nicely because one likes to lose and the other likes to gain. The metal loses electrons to become a cation. Remember, a cation is just an ion with a positive charge. The nonmetal gains electrons to become an anion, which is just an ion with a negative charge. The example I have shown below is between sodium and chlorine. Sodium is the metal ion, so you can see its little purple electron here. It's going to donate that purple electron to chlorine, so it's going to give it away. This makes sodium have a positive +1 charge because it lost 1 electron. So it's a cation now. The chlorine, notice the chlorine has 1, 2, 3, 4, 5, 6, 7. It has 7 electrons. We said it wants 8, an octet. So that's why it takes that 1 electron from sodium, so that now chlorine, on the product side here, has 8 total electrons. So that's what its goal was. But since it gained an extra electron, it's going to have a -1 charge, because electrons are negatively charged. So now we have a positive cation and a negative anion, and what holds them together is the attraction of those opposite charges. So ionic compounds, we said, formed between metals and nonmetals. Sometimes the nonmetal portion is in the form of a polyatomic ion. So I just want to introduce polyatomic ions now. We're going to use these later on when we start naming chemical compounds. So I want to point out the polyatomic ions, they consist of 2 or more atoms bonded covalently. But since they have a charge, so notice all of the ions in this table have a charge, either -1 charge, -2 charge, or a +1 charge. So since they have a charge, since they're cations and anions, they are part of ionic compounds. And I point this out because what we're going to look at next is a summary of all type of bonds. So looking at the summary, how do you tell if it's an ionic compound? Well, there's several different types. We talked about metals and nonmetals forming. So if you see a chemical formula with a metal and a nonmetal, and we can now recognize based off the periodic table and where those elements are, if it's a metal or a nonmetal. So if a metal and a nonmetal are together, that's an ionic compound. But sometimes we'll also see a metal with a polyatomic ion, and that's that list you saw on the previous page, the previous slide. So you can have a metal with a polyatomic, or you might have a polyatomic with a nonmetal, or even 2 polyatomics together. So those are all the different types of ionic bonding that we'll see. We're actually going to go through and name all of those types next week in the second part of Chapter 7. For covalent compounds, how do you recognize those? If two nonmetals are together, so a nonmetal with a nonmetal. Also, we'll see covalent compounds in this class when we have a nonmetal with a metalloid. Once again, using where those elements are on the periodic table to figure out if they're a metal or a nonmetal.